Alright, today's talk is about water movement in soil. My name is Doc. Okay, now let us look at Darcy's law. Okay, so we have a figure here. Figure 3.3 shows a soil column experiment illustrating Darcy's law in the horizontal direction. So we have a soil column with the length of L. We place it horizontally. There is a water entering from the left side. Okay, and the water exiting at the right side. Okay, so the reservoir in the P1 in the left side is being raised to P1, and the reservoir in the right side is being lowered to a height of P2. So P1 is actually greater than P2, so the water will flow from left to right. Okay, and this soil column has a cross-sectional area of A. Cross-sectional area basically means luas kelatan rentas. Okay, and because the water is flowing from left side to right side, and that is a volumetric flow rate. Okay, volumetric flow rate here is measured by using the graduated cylinder, taking the accumulating the water leaving at the reservoir at the right side over time, so you can get the volume. And then the time, if you record, then you can also get the time. So you can get the volume, and with time, with that you can get the meter cube over second. Okay. So so the flow rate is equals to the Ks, the saturated hydraulic conductivity, the area, the cross-sectional area, the difference of P. The difference of P is actually the P1 minus P2, the hydrostatic pressure. Okay, in head difference, and the L is the horizontal difference, the horizontal length of the soil column. So Q is in flow rate, is meter cube over second. Okay, it's measured by using the graduated cylinder that measuring the water leaving the reservoir at right side. Okay, and the Ks is the saturated hydraulic conductivity. Saturated hydraulic conductivity has a unit of meter over second, and A is a cross-sectional area. It has a unit of meter square, and changes of P is equals to P1 minus P2, which is the hydrostatic pressure head difference. It has a unit of meter. Okay, and the L is the horizontal distance. It has a unit of meter. All right. So if you take the Q and divided by the area A, so you will get Ks. You will get saturated hydraulic conductivity multiplied with the hydrostatic pressure head difference, and then divided by the L, which is equals to the Jw, which is called the water flux. So the water flux has a unit of meter over second. So you can see that the changes of P is in the unit of meter, and the L is also having the unit of meter. So meter divided by meter, you get 1. So Ks is the meter over second. So here, the whole variable here, you only get meter over second. Then of course, Jw, the water flux, is also meter over second. And always keep in mind that your coordinate directions. So when it's horizontal, from left to right, we define it as a positive. Okay, from bottom to top, we define it as a positive. So from left to right, we define it as positive if the flow is happening from right to left, then the flow will be negative. So if the flow is happening from bottom to top, is positive. If the flow is happening from top to bottom, then it will be negative Z. So horizontal from left to right, positive X. From right to left, it will be negative X. Okay. So horizontal flow Jw equals to negative Ks P1 minus P2 and X1. Okay, X1 minus X2. So imagine the flow here from P1 minus P2. So there will be X1 minus X2. So X1, if you look at the coordinate X1, X1 is somewhere here, X2 is somewhere far away. So X1 minus X2, of course the X1 value is smaller than the X2 value. As a result, you have a negative value. So we have a negative value here to cancel out the negative value given by X1 minus X2. So that's why we have a negative in here. So Jw, horizontal flow, is negative saturated hydraulic conductivity, Ks, P1 minus P2, the hydrostatic head difference, divided by x1 minus x2. All right. For vertical flow, the JW, the water flux, is equals to negative kx h1 minus h2 and z1 minus z2. So similarly, we have a negative here because if you take z1 somewhere here and the z2 somewhere above here, of course z2 is greater than z1. As a result, z1 minus z2, you get negative value. So we need to have a negative value here to cancel out the negative value produced by z1 minus z2. Okay, so vertical flow JW, the water flux, equals to negative saturated hydraulic conductivity multiplied by in the bracket h1 minus h2, okay, divided by z1 minus z2. So h1 include the elevation of the water, as well as the elevation of the soil. So h1 equals to p1 plus z1 and h2 equals to p2 plus z2. And then of course z1 z2 are vertical location from the same reference point. So you must have a same. You must pick a reference point. It doesn't have to be similar to z1 and z2. It can be anywhere, but you must have a reference point. So the z1 and z2 will refer to the reference point, and x1 and x2 are horizontal location. So you must also have a reference point, but you can pick either x1 or x2 as a reference point. Okay, so let's look at table 3.1. The table 3.1 shows the procedure for using Darcy's law in vertical flow problem. So step 1, define a reference elevation. So we must pick a point of reference. And then step 2, determine 2 points, point 1 and point 2, where the hydraulic head h is known. Okay, and step 3, calculate the gradient. So in bracket h2 minus h1, and then divided by in bracket z2 minus z1. And then step 4, you plug into equation 3.14. So if you look at the previous slide, so we have a h1 minus h2 and z1 minus z2, but here you show h2 minus h1 and then z2 minus z1. So basically it's the same thing, it's just that the numbering is different, but you can still plug into this equation and you can use to calculate the vertical flow. In this case, the ZW is water flux. Okay, now let's look at example 3.1, a 100 centimeter soil column. Okay, so we can have, here we have a 100 centimeter soil column. So 100 centimeter is filled with soil, and the soil is filled in the column. So you call it soil column. So 100 centimeter soil column containing packed sand. So inside the soil is a type of soil is sand. The texture is sand with saturated hydraulic conductivity of 100 centimeter per day. So the saturated hydraulic conductivity is given as 100 centimeter per day. All right. And is placed vertically with the bottom open to the atmosphere. So if bottom, see the bottom is open to the atmosphere, means the pressure at the bottom is 0. All right, bottom is pressure at the bottom is 0. So a constant 10 centimeter height of water is ponded continuously on the top surface. So they provide a 10 centimeters level of water, and the level is 10 centimeter all the time. So the constant height of water. Okay, so then you are asked to calculate the steady water flux JW through the soil. Okay, so when you define the reference, of course here is easier to define the reference Z1 at the bottom. So Z1 is defined as the reference. Since we define as reference, you get a 0. Z1 will be equal to 0. And then because it's open, the bottom is open to the atmosphere, the pressure is also 0. We know that H1 is given by P1 plus Z2, P1 plus Z1. So P1 is actually the elevation of water, and Z1 is the height of the column. So if you look at here, okay, there is no 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 elevation of water at point 1. So of course P1 will be 0 because no water, no pressure, the pressure will be 0. So Z1 is the elevation which we define as 0. So Z1 plus P1 plus Z1 equals to H1, which is equals to 0. Okay, that's what it means. And if you look at Z2, okay, Z2 is 100 centimeter above Z1. So Z2 obviously is 100 centimeter, okay, because the length of the column is 100 centimeter. And P2 is the pressure due to water at this point, and here is 10, okay, 10 centimeter. So we have a 10 centimeter here. And of course H2 is the sum of P2 plus Z2. Here we get 10 plus 100, you get 110 centimeter. All right, so with this kind of information, you can calculate the vertical flow by using this equation. JW, water flux, equals to negative Ks, negative saturated hydraulic conductivity, multiply with the bracket H1 minus H2, okay, H1 minus H2, and Z1 minus Z2, okay, Z1 minus Z2. So you might want to ask me, can I use H2 minus H1 and then Z2 minus Z1? The answer is yes, you can do that because it's the same. It doesn't matter whether you change the numbering or not. It's always the same. The visual value is always the same. All right, so let us continue the calculation. Okay, so JW equals to negative, okay, 100 centimeter per day for the saturated hydraulic conductivity. P1, so the H1 equals to P1 plus Z1. P1 is the pressure of water. So if that's water, if that is a ponded water, then you will have the P1. And then Z1 is the elevation of the soil, okay. And then minus H2. H2 is given by P2 plus Z2. And of course Z1 minus Z2 at the bottom. All right, so we can know that P1 is actually 0, and Z1 is also 0. So 0 0 minus P2. The pressure is 10 centimeter, and the height of the column, the height of Z2 is 100 centimeter. All right, and then divided by Z1 0 minus Z2, which is 100, and then if we continue the calculation, we'll get negative 110 centimeter divided by 100 centimeter, multiply with 100 centimeter per day of saturated hydraulic conductivity, and you have a negative sign here, and then finally you get negative 100 centimeter per day. So the negative sign means opposite direction of positive Z. Okay, that means that it is downward flow. So our definition is that it is positive upward. Okay, it is positive upward. So since we get a negative value, basically means that the flow is not flowing up, because flowing up the value has to be positive. Since we get a negative value, means the flow is against the positive value, so it's flowing down. Okay, that's what it means. Thank you. Okay, now let us look at example 3.2. The example 3.2, assume that the soil column in example 3.1 is placed horizontally. So we know that in example 3.1, the column was placed vertically. Now we want to place it. We want to place the same column. We want to place the same column horizontally with 10 centimeter of water ponded over the left side, while the right side is open to the atmosphere. So calculate the flow through the column. So horizontal flow, JW, water flux, equals to minus saturated hydraulic conductivity, the hydrostatic pressure head, P1 minus P2 over the X1 minus X2 distance. All right. So so we know that water flux equals to negative, where the saturated hydraulic conductivity is 100 centimeter per day, and the P1 is the water ponded, which is 10 centimeter, and the P2, which exposed to the atmosphere, we have 0 centimeter, and the the X1, it is take as a reference point at 0 centimeter, and because we always start counting from the smallest to the highest, so X1 0 centimeter, X2 100 centimeter. So with that, you can get 10 centimeter per day. So since it's positive sign, means that the flow is in the directions of x, positive x. Okay, so flowing from the left to the right, so flowing in the positive x direction. Okay. Okay, now let's look at the measurement of saturated hydraulic conductivity. Okay, we can use a method called constant head method. Constant head method is one of the methods that can be used to measure the saturated hydraulic conductivity. So easy to measure the water flux, okay, in a laboratory column experiment, because we can actually gather the water that leaving the soil column at the bottom. We just measure the volume leaving the soil column over time. And then we can calculate the volume meter cube over time, which can be the second or minute or hour. Okay, so we can calculate the JW, the water flux. Okay, Darcy's law may be used to measure Ks. Okay, so our intention here is to measure the saturated hydraulic conductivity Ks. Okay, back here again. So we want to measure the Ks. All right, the Ks. All right, so we can rearrange to have a Ks on the left side. So is where Ks equals to negative water flux divided by the hydraulic gradient, the H1 minus H2 divided by Z1 minus Z2. Okay, and then we can rearrange this again into JW bracket Z1 minus Z2 divided by H1 minus H2. All right, so we can refer back to the example that we did just now, and we can try to label that. We can try to replace the variable with a symbol. Okay, so take Z1. Okay, Z1 equals to 0 because it's a reference point. So Z2 is the L. Z2 is here. So this the vertical length height, which is L. So we take Z2 as L. H1 is P1 plus Z1, the hydrostatic pressure head, and plus the elevation. So the elevation of the soil. So here P1 is 0. Z1 is also 0. So 0 plus 0 we get 0. So H2 is P2 plus Z2. In this case, the P2 is actually the standing water, the hydrostatic pressure head meter. So we place it with P, and the Z2 is the height of the soil column, which is L. So here is the definition. B is the standing water height above the soil column. So if B is here, so here is the soil surface. So you have a water standing on top of the soil, and the height of water is B. Okay, it's given as B, right? And the L is the vertical column length. So vertical column length is L. Okay, so referring back to this equation, so Ks now is equals to JW in bracket the Z1. We know that Z1 is 0. And the Z2 is L, so it's minus L, and divided by H1 minus H2. The H1 is what? H1 is 0. Okay, H1 is 0. Okay, so 0 minus H2. H2 is now B plus L. So in bracket B plus L. So we can simplify the equation further, and we'll get the saturated hydraulic conductivity equals to negative water flux multiplied by the length of the soil column divided by the height of the standing water plus the length of the soil column. So you can see that there's a negative sign here. Negative sign means flow is opposite Z, positive Z. So positive Z is upward flow of water, so upward flow. So since it's negative, this means that the water flow is downward. So it's against the positive Z. So it means that the water will flow downward. Okay. Alright, so here is the second method to measure saturated hydraulic conductivity. The second method here is called falling head method. So water is initially ponded to a height, okay, BO. Okay, initially it's BO. The height is BO, okay, above the saturated column, and is allowed to fall with time as the water flow out the bottom where P equals to 0. So the water initially is B node, height of the water, okay. Sorry, the water height is initially BO, right? So the water is allowed to flow through the soil column, and when the water flow through, the water level will drop, so it become B1, okay, B1, okay, B1. After it's dropped, it become B1, okay. So and the bottom here is exposed to the atmosphere. So the pressure is the the hydrostatic pressure head is in meter is still 0. Okay, so by using the same definition we have in the previous method, we can derive it for the falling head method to estimate the saturated hydraulic conductivity. So if you look at the equation, so I'm not going to talk about the derivation to make your life easier. So I only show you the equation here. So saturated hydraulic conductivity equals to the length of the soil column divided by the time. So let's say we let the water flow through. For how long we let the water flow through? Okay, so we must know the time, and then we must know the initial height. The initial height is B0. Okay, and then the final height of the water is B1. Okay, so if you leave it for 10 seconds, what happened after 10 seconds? So the water that left is B1. Okay, so B1. So and of course plus L. L is the length, which is the same all the time. So we're using this formula, we can determine the saturated hydraulic conductivity by using falling head method. Okay. Okay, now let us look at example 3.3 regarding the falling head method. So we have 100 centimeter long soil column is saturated, and 10 centimeter of water is ponded over the top at t equals to 0. So the BO is 10 centimeter. Okay, and the L is 100 centimeter. So the time when it is 10 centimeter, it is T0 in the vessel that has same cross-sectional area as the column. At t equals to 1 hour, the height of the overlying water has fallen to 5 centimeters. So after 1 hour, the BO, which is 10 centimeters, now become 5 centimeters. So now we are asked to calculate the saturated hydraulic conductivity in centimeter per day. So we use the formula given to us in the previous slide. So we can place in the value. So L is 100 centimeter, L 100 centimeter, L 100 centimeter, L 100 centimeter, and the T after 1 hour. So we put here T 1 hour, and then the BO initially is 10 centimeter, so we put 10 centimeter, and then the B1 after 1 hour you get 5 centimeter, so you put 5 centimeter here. So you can use that to calculate. In the end, you get the saturated hydraulic quantity. The saturated hydraulic conductivity is equals to 111.65 centimeter per day. Okay, so I hope there's no problem to convert 1 hour to day. So for example, 1 day has 24 hours, so you take 1 hour divided by 24, so you will get 1 day. So 1 divided by 24, you get 1 day. So at the bottom you take 1 divided by 24. Okay, so then you can convert it to day. All right, now we're talking about the water flow in unsaturated soil. So okay, unsaturated soil basically referring to soil that is partially filled with water, or in Bahasa Malaysia we call it tanah separa tepu. Okay, so the water pressure within the liquid phase is caused by water elevation. So if you have any height of water, and then the attraction to solid surface, so this is due to the daya tarikan. Okay, daya tarikan to particle tanah. Okay, so the surface tension of air-water interface. So this the forces between the air and water interface. Okay, so we have surface tension, and because of the effects of surface tension and solid surfaces, the liquid pressure is lower than the reference liquid pressure at the same elevation. So basically it means that because of surface tension and solid surfaces, there appears to be some kind of suction pressure happening in the unsaturated. Okay, now let us look at Buckingham-Darcy's law. Okay, Buckingham-Darcy flux law. Okay, so this law is used to govern unsaturated flow. Okay, unsaturated flow. Okay, means water flow in unsaturated soil. So two assumptions. So the first assumption, driving forces for water flow in isothermal, so it means temperature is constant. Rigid means the soil does not expand or contract. Okay, unsaturated soil containing no solid membrane, zero air pressure potential. So driving force is based on the sum of metric potential and gravitational potential. Right. The hydraulic conductivity of unsaturated soil. So here we define the hydraulic conductivity as unsaturated hydraulic conductivity. Okay, so it's a function of water content or metric potential. So it can be either one. Okay, so water content theta L, metric suction WM. Okay, for vertical flow is it is derived as oriented positively upward, so it is expected to flow upward based on the orientation of the equation, right? So the JW water flow, JW equals to negative unsaturated hydraulic conductivity, so it's K as a function of metric suction, okay, and then multiply by the derivative of H over the derivative of Z, okay, so it's a spatial derivative of H, then equals to minus K as a function of metric suction, and then the derivative H here, the H here is given by metric suction plus Z, which is the elevation, and together they are called hydraulic head, okay. So of course hydraulic head has a unit of meter, and the unsaturated hydraulic conductivity has a unit of meter over second. Alright, and the JW, which is the water flux, has a unit of meter over second. So, and then this now the H becomes metric suction plus Z, the elevation. So if you take the derivative of these separate variables, you will get delta Wm over delta Z plus 1, because derivative of Z over Z is actually 1, right? And this derivative is a function of time and also spatial. All right. So since we want to evaluate this derivative at constant time, means that the derivative is evaluated at a particular time at constant time. Okay. Partial derivative indicates transient time-dependent flow. Okay. So in steady state, the partial derivative reduces to ordinary derivative, so you get dWm over dZ, right? Okay, now let's look at unsaturated hydraulic conductivity. So K as a function of metric suction. So here's a diagram. It's a figure 3.9. Shows a typical unsaturated hydraulic conductivity with metric potential function for a coarse textural sandy soil and a finer textural silty soil. So you can see that at different metric potential or different metric suction potential, you get a different unsaturated hydraulic conductivity. So for example, you look at sand, initially it's very high, but as the metric potential increases, the unsaturated hydraulic conductivity drop more dramatically than silt. So silt, you can imagine that silt has a coarser size. Silt has a smaller size compared to sand. Okay. Okay, so unsaturated hydraulic conductivity, which is a function of metric suction, is non-linear function of water content or metric suction. At saturation, coarse texture soil has higher conductivity. As you can see, coarse texture soil, sand, has higher conductivity than finer texture because of larger pore spaces. So sand has a larger pore spaces. As a result, it has a higher unsaturated hydraulic conductivity. These large pore spaces produces dramatic decrease in unsaturated hydraulic conductivity in sandy soil. So eventually, sandy soil has a lower unsaturated hydraulic conductivity than silt loam. So because it has a larger pore, it will dry quickly as the pressure increase, as metric suction increases. So as a result, it drops quickly. So then now the hydraulic conductivity become lesser than the one that's finer. So silt now become larger. Okay. So silt soil at high metric suction could retain more water and a greater number of fill pore than sandy soil. Okay. Okay. Now let's look into another example. So now this is so this is example 3.9. Okay, example 3.9. So this is a 50 centimeter high soil column. So 50 centimeter. Okay, 50 centimeter high soil column. Okay, it's placed above a water source, maintaining the bottom of the column Z equals 0 at saturation 0. Okay. Okay, so the bottom of the column in touch with the water. So you have a column which is 50 centimeter. Okay, 50 centimeter, and then then at the bottom of the soil you have water, okay, come in contact with water. So this is the soil, right, 50 centimeter, right? That's what it means. So the pressure here, Wm equals to 0. So it means it's atmospheric pressure, okay, atmospheric pressure. So the Z start from here, Z0. So here the Z50, all right, okay. Okay, so at the top of the column is Z50 is exposed to constant evaporative condition. So the water is allowed to evaporate, okay, evaporate out, okay. Okay, and it's a constant evaporation. So EA, okay, EA is a constant. Okay, constant evaporation. And then what else? Tensiometer are located at Z10, okay, at 10, 20, 30, 40, and 50. Okay. Okay. So 10 is 0, 20, 30, 40, and 50. Okay, centimeter. Okay, that's where the tensiometer are being located. Okay, so the tensiometer placed inside the column is to measure the pressure, the metric suction. Okay. Sorry, 50 we don't have tensiometer. We only have 10, 20, 30, and 40. Okay. The evaporation rate E in steady state when the tensiometer and water flux do not change with time is equal to the flux through the column and is measured by the rate of water entry per unit area into the column from the water source. Okay, so the water enter here will be the water that leaving at the top. Okay, the water that enter from the bottom will be equals to the water leaving the top. At steady state it will be equal. Okay, in steady state the tensiometer reading are shown in table 3.3. so this is table 3.3, and the evaporation rate is 0.5. okay, so the evaporation rate is 0.5 centimeter per day. All right, so now, so what we need to do here, we need to calculate the unsaturated hydraulic conductivity, okay, from this table given at steady state. So we can, what can we do? We plot it again. That centimeter, 40, 30, 20, 10, and 0. So we have Z1, Z2, Z3, Z4, and Z5. Okay, and then of course we have also this metric suction. So this is this value is metric suction. Okay, suction is centimeter, and here we have negative 125, negative 75, negative 40, negative 15, and 0. All right, so to find this this unsaturated hydraulic conductivity, so we need to know that the ZW equals to K, unsaturated hydraulic conductivity, all right, multiply with the change of hydraulic head. Okay, and this is equivalent to sorry, negative. This is equivalent to H1 minus H2, okay, and Z1 minus Z2. Of course, the H1 is equals to Wm1 plus Z1, and of course the H2 Wm2 plus Z2. Okay. All right. So because we know that the flux out from the top of the column is actually equals to the evaporation, so we can use evaporation here is centimeter per day. Okay, centimeter per day, right? So we can actually rearrange this so that we can find K. We can try to find K, okay, right? So the K is given by negative E over H1 minus H2 divided by Z1, Z2, right? So this is the equation we need to use in order to find the unsaturated hydraulic conductivity. So let us continue with the calculation. So since we have Z, okay, we have the metric suction. Now we have to calculate the hydraulic head. Okay, hydraulic head in centimeter. Alright, so we can take negative 125. Okay, so this case we can assume it as a Wm1 plus Z1, which is equals to negative 125, okay, plus 40, okay, which is equals to negative 85, right? So here is negative 75 plus 30, which is equals to negative 45, okay, and here is negative 40 plus 20, so it's negative 20, okay. Now here is negative 15 plus 10, so it's negative 5, and here is 0 plus 0 equals to 0. Alright, so once we have H, we can find the difference of hydraulic head, centimeter, okay, centimeter. So let me see. Oops. We know. Okay. Back to here. Okay. H centimeter. All right. So we're going to find the difference. The difference here is given by H1 minus H2, which is negative 85, minus H2 is negative 45, so we get negative 40, okay, negative 40, and then of course H2 minus H3, which is negative 45, minus negative 20, which is equals to negative 25, okay, negative 25, and we do the same for the flowing. Okay, so I need to arrange this a little bit so that there is a space between them. Okay. So here is negative 20 minus negative 5, so we have negative 15, okay, negative 5 minus 0, negative 5, okay. Right, now you can find the hydraulic gradient H divided by Z, okay, hydraulic gradient here is negative 40 over 10, okay, here is negative 25 over 10. So the 10 is given by, maybe I should write this so you can see it more clearly. Okay, you can see more clearly. So it's negative 40 divided by H1 minus H2 divided by Z1 minus Z2. Okay, so we get negative 40 minus with 40 minus 30, so we get negative 4. Okay, and here is H2 minus H3, Z2 minus Z3, so we get negative 25 minus 30 minus 20. Okay, so it's 30 minus 20, so we get 10, so we get negative 2.5. And here is negative 15 divided by 10, you get negative 1.5. Here is negative 5 divided by 10, you get negative 0.5. Right? So with that, we can calculate the unsaturated hydraulic conductivity. Okay, unsaturated hydraulic conductivity. So this is done by taking the E divided by the hydraulic gradient. So in this case, it's negative 0.5 divided by negative 4. So what do you get? You get 0.125. Right? So and this one is 0.5, negative 0.5 divided by negative 2.5. You get 0.2. Okay, you get 0.2. Okay, and here is negative 1.5 divided, you get negative 0.5 divided by negative 1.5, and you get 0.33. Alright, and here is negative 0.5 divided by negative 0.5, so you get 1. Right? So the metric section, you have to calculate the metric section. Okay, metric section. The metric section is basically taking both of them, negative 125. It's as simple as Wm1 plus Wm2 divided by 2. So it's negative 125 minus negative 75 divided by 2. So what do you get? You get you get this one, you add together, you get negative 100. Okay, so the next one is negative 75 minus negative 40 divided by 2, so that gives you 57.5 negative. Okay, the next one is negative 40 minus negative 15 divided by 2. This one should give you around negative 27.5. And the last one is negative 15 plus 0 divided by 2. So you get here negative 7.5. Right? So now you already calculate, so you know that K, so that you can make a summary of this. Okay, make a summary. Z centimeter. Okay, of 40, 30, 20, 10, and 0. Okay, and okay, sorry, this is not right. It's not right. You can write as Z centimeter So at 35, at 25, at 15, at 5. Okay. Oops. Okay, so we can write as a K, oops, K matrix suction now is given by 0.125. Okay, so the value is in centimeter. Is it correct? Centimeter per day. Okay, centimeter per day at a metric suction of negative 100 centimeter. Okay, the next one is 0.2 centimeter per day. Happen at 57.5 centimeter metric suction. The other one is 0.33 centimeter per day. Happen at 27.5 centimeter metric suction. And the last one is 1 centimeter per day. Happen at negative 7.5 centimeter of metric suction. So here is the answer that we are looking for. Okay, thank you. Alright, now let's look at the steady state downward water flow through a crop root zone. So the steady state rarely occur in unsaturated soil, particularly in the field. This is because temperature, evaporation, water uptake, irrigation, and other processes that affect water transport tend to be influenced by diurnal circles of radiant energy to Earth's surface. So imagine that the soil surface is cold in the morning, become very warm in the afternoon, 12 noon, and then become cold again at night. So that's kind of diurnal changes. Okay, daily changes from cold to warm and warm to cold again. So because of this, we rarely get a steady state at the soil surface. So because soil surface is mainly unsaturated soil, so unsaturated soil rarely at steady state in this regard. So the external influences are repeated at a regular interval at approximately the same intensity that varies mostly at the surface and become relatively steady below it. So the external influences, for example, the temperature due to sunlight, things like that, happen on a daily basis. So it varies mostly at the surface, but as we go deeper into the soil, the temperature in the soil at the deeper soil would remain at a relatively constant over time. The same goes with the soil water content as well. Okay, let us look at example 3.10, a fully developed crop root zone extending from z equal to 0 at the surface to z equals to negative L into the depth of soil is irrigated daily at the irrigation rate of I0. Okay, so the irrigation rate is I0. Water uptake within the root zone is spatially and temporally uniform at a rate of RW, and the total removed each day is equals to the evapotranspiration ET, and the ET is less than the irrigation rate. So now calculate the steady water flux as a function of depth. Okay, so you can so you know that the RW is the root water uptake rate is a meter cube over meter cube per second, and ET is the evapotranspiration is meter per second, and I naught is the water irrigation rate is a meter cube over meter cube per second. So we can write a simple differential equation minus dJW, the water flux, divided by dz. Z is the elevation within the soil, and minus RW. RW is the root water uptake rate, and then equals to 0. So you can represent the the root water uptake rate with evapotranspiration, and then divide it by the length of the root L. Okay, hence you can write this equation into this form, and then you can rearrange it for integration. So you can integrate from the rate of the initial stage where the water is being provided from the irrigation, and then it's also the place where Z equals to 0. At Z equals to 0, the irrigation rate is I naught. The I naught is exactly the rate, is a water infiltration rate, and then you can integrate to a depth Z, the unknown Z that you want to calculate, the steady flux, the steady water flux as a function of depth. So the depth is Z, so you integrate it to a depth of Z, and then you define it as a water flux JW. So in this way, you can get an equation for JW equals to infiltration rate I naught minus evapotranspiration divided by the length of the length of the plant root, and then multiply with the depth of the soil. Okay, so this is the Z, of course, is less than L. Okay. Right, now let's look at the water conservation equation. Okay, so we are looking at the governing equations of water flow. Okay, so metric potential and water content are functions of space and time. This is known as transient or time dependent. Okay, complete transient water flow description is to specify the water conservation equation, also called the mass balance or continuity equation. So not Paul scale modeling, but volume average descriptions of water conservation. So the analysis on the cube of soil occupying a volume V equals to the changes of X, volume V equals to a small volume of X, small volume of Y, and a small volume of Z at a point X, Y, Z in the flow field of porous medium. So we only account for a small cube in this respect. Okay. For simplicity, assume water flow in Z direction, homogeneous and unsaturated soil. So we can account for X, Y, Z, but for simplicity reason, we only derive the equation for Z directions, and it's assumed as a homogeneous. So now show you this diagram. Show you the unit volume of soil used to derive the water mass balance equation. So unit volume basically means a small volume of X, small volume of Y, and small volume of Z. So this cube, okay, it has an input coming in, a water inflow rate, okay, coming in, the water flux coming in, and also the water flux going out, okay, water flux going out. And it has a flow area, an area which is given by small changes of X multiplied with the changes of Y. So you get an area. All right, and of course this is a cube. It has a soil water storage. Okay, it has a soil water storage. All right, and and of course this volume, this cube can also lose water through water extraction rate. This water extraction rate is actually the loss due to plant root obstruction. Okay, so the root of the plant extract the water from the cube. So the water in the cube was lost in this regard. So not only incoming water can supply water into the cube, and not only the outflow of water that can lose the water from the storage, but also the root of the plant can also extract water from the cube. All right. So that's basically the whole principle behind the mass conservation equation. All right. Okay. So here is the step that needed to derive the equation. The governing equation of water flow in unsaturated soil. But I'm not going to go into the details. But if you follow the step, you should be able to arrive at this partial differential equation. So if you look at this partial differential equation, basically it shows the spatial variations of water flux, and also take into account of the root obstruction, and then equals to the changes of volumetric water content in the cube. So in the previous slide, you can see there's cube. So this cube shows the input, output. So the influx and outflux is basically the JW, and then there's obstruction of RW due to root water absorption, and then there's also a storage. okay, the storage given by theta L. So this equation basically summarize the whole processes happening within the cube, okay, right? So we can rearrange this equation into here. So you can get a spatial derivative of water flux plus water storage variation with time, and then and also the effects of root water absorption, and then equals to 0. So this is one-dimensional equation, and of course we can expand this equation into three-dimensional. So you only have initially we only have we only have z, and now we include x and y into the equation. So end up we have a three-dimensional flow equation for soil, okay, soil water content. Okay, so the equation that we derived from the previous slide, now it can be used to for further expansion, and so that we can come to a more specific equation. So the specific equation that we're going to talk about is the Richard equation. So the Richard equation can be used for transient water flow in unsaturated soil, right? So this is the governing equation that we derived in the previous slide for the mass balance for a cube soil, okay? And now we can include the flux term, the flux term that we've been using to calculate the unsaturated hydraulic conductivity. Okay, so it's water flux equals to unsaturated hydraulic conductivity, which is a function of metric suction, and then we have in the bracket is a spatial derivative of the metric suction plus 1. So basically plus basically means it's oriented upward, and then you have 1 here. This is the effects of gravity, okay, gravitational, okay. Now we have this JW, the water flux. The water flux can be included into the governing equation JW, the spatial derivative JW. As a result, we have a new equation, looks something like this, and then we can take this root water absorption as equals to 0. As a result, we can rearrange this equation again into this form, and then we can simplify. We can take out the negative sign from here to here, so negative become positive. So we get something like this, a new partial differential equation, and this is known as a mixed form of Richard equation. The reason it's called mixed form because here you have a metric suction, and then at the storage you have water content. So you have a mixture of metric suction and water content in the governing equation. So that's why you call it mixed form Richard equation. So in general, this is also known as a Richard equation. Okay. And then we use the chain rule to expand the spatial derivative of metric suction. So the spatial derivative of metric suction can be expanded to include the effects of volumetric water content. Okay, volumetric water content, and also the unsaturated hydraulic conductivity, which is a function of metric suction. Now, the metric suction itself is also a function of water content. So metric suction and water content, these two are related by the name called water characteristic curve, if you still remember that we talked about in the previous chapter. So now you can take unsaturated hydraulic conductivity as a function of water content. In this case, they are similar. All right. And now, of course, now we can change the unsaturated hydraulic conductivity, which is a function of metric suction. Now we can change it to unsaturated hydraulic conductivity as a function of water content. And then, of course, we include the chain rule effect after the spatial derivative of metric suction. So we have a new form, something like this. And then, of course, we can take this K, theta L, and also the water content derivative of metric suction combined together, and we call it dW theta L, which is known as soil water diffusivity, and therefore we have a new form of Richard equation, and this new form of Richard equation is known as water content form of Richard equation. Because why? Because we have water content in the equation. Okay, water content in the independent variable, and also water content in the dependent variable. So this is called water content form of Richard equation. right? To solve this equation, we need two boundary conditions. So you look at here, you see this is z direction. Z direction basically means referring to the vertical soil. Okay, so we need two boundary conditions, one at the top soil and one at the bottom surface. Okay, top surface and bottom surface, and also the initial condition describing the water content of the entire profile at time t0. So at time t0, we need to know what is the water content distribution, soil volumetric water content distribution within the soil, and we need to know what's happening at the lower boundary and what's happening at the upper boundary. So we need to know the water content at the upper boundary. We also need to know the water content at the lower boundary, as well as the distribution of water content within the soil itself. Okay, in order to solve this equation. Okay, there are also some limitations with the Richard equation. Okay, the mix and water content form of the equation ignore hysteresis. Hysteresis, remember the one that we talked about in the previous chapter, the wetting and drying, the water characteristic curve, they are not the same. All right, they are not the same. So this equation does not take that into account. So the derivative of metric suction with respect to volumetric water content is defined only for a uniform wetting or drying process, in which volumetric water content is described uniquely by a single curve. We know that that's more than one curve because of the wetting and drying, they are different. So when repeated wetting and drying cycles are present, the equation becomes invalid and the water diffusivity dW theta L cannot be defined. Okay, so let's look at another forms of Richard equation. So there's another form which is called metric potential form of Richard equation. So this is a Richard equation from a previous slide, and if we can use the chain rule, we can change the water storage, the water storage, the changes of volumetric water content with time. Okay, so we can change it to include the effects of metric suctions. Okay, at the storage side, and then of course we gather this derivative of theta L over Wm, and we call it as a Cw Wm is called as a water capacity function. So it is equal to the inverse slope of Wm theta L, and it has similar limitation as mix and water content form Richard equation. Okay, now let us look at the water capacity function. Water capacity function is Cw Wm. So Cw Wm is a water capacity function. So the figure 3.14 shows the metric potential water capacity relations for the prototype sandy loam and safe soil provided in the Hydrus 1 code. Okay, so Hydrus 1 code basically is a simulation model. Okay, right. So the plotting can see that the increase of a sandy loam to a very high point for the Cw Wm, and then it dropped dramatically to a lowest point. So it's almost zero at saturation, and as the metric suction increases, it reaches a peak and then drop dramatically until as the metric suction increases to a very high value. Whereas a small increase in the water capacity for silt, and then gradually reduces over the increase of metric suction. All right. So the Cw Wm equals to the derivative of metric suction. The metric suction derivative on the water content. So this increase in metric potential per unit increase in water content. So the largest value of this water capacity function are associated with the wet end of the capillary region of the retention curve. So where the larger pore are emptying with the modest changes in the suction, right? And the C and the water capacity function is zero at saturation. So at saturation, it is zero. It approaches zero at extreme dryness, where enormous changes in the suction occur with small changes in the water content. So at extremely high suction, the water capacity also zero, right? So that's what it means. Okay, so let's look at the model functions form. It is called model function form, or sometimes it's also called constitutive functions, or also known as supporting equation. So you see, we have these equation functions, metric suction with respect to as functions of water content, and unsaturated hydraulic conductivity as a functions of water content. So there are two models shown here, Brooks and Corey in 1964 and Van Ganifton in 1980. So these are very old equations derived at a different time. And you can see there are metric suction as a functions of water content. So we have these forms of equation, and then for Van Ganifton we have a different form. And then this equation and this equation separately. So this equation can be used to derive the unsaturated hydraulic conductivity. Similarly, this equation can also be used to derive this equation. Alright, so these two equations can be used as an input into the Ricci equation. Similarly, this equation can also be used as a input into the Ricci equation. That's why it is called supporting equation, because it supports the main equation, the Ricci equation, or it's called constitutive function. Or of course, here it is known as model functions form. Right? So equation 3.84 for k theta L. Okay, equation 3.84. Okay, 3.84 in Van Ganifton model was derived from equation 3.8. So 3.82, this equation is used to derive the unsaturated hydraulic conductivity equation for to get this form. Alright, using theoretical model of Molem. Alright, similarly, equation 3.83 was derived from 3.81. Right, so they are in fact related to one another. 3.81 and 3.83 are related, and 3.82 and 3.84 are related. Okay, so the methods to determine parameter in hydraulic property functions. First, determine by curve. First method you can use. It can be determined by curve fitting appropriate equation to measure water retention data. So determine by curve fitting appropriate equation to measure water retention data. So if you conduct experiment, so you can do curve fitting on your data, so that you can estimate the alpha, the n and m. Or if you use Brooks and Corey equation, then you can determine the ht and lambda. Okay, so inverse method by second method is an inverse method by fitting numerical solution of Ricci equation to one multiple outflow data. So you can use this curve fitting method, but this time you're using this Ricci equation in a computer simulation, and then you try to change the model parameter to match with the output simulation. All right. And the third method is determine hydraulic function parameter by applying analytical solution of Ricci equation to horizontal infiltration data. Okay, so this is another alternative. Okay. Also, I would like to talk about a little bit more about the variable here. For example, you have this variable equals to this bracket volumetric water content minus residue water content divided by the saturated water content minus with the residue water content. Okay, so and this equation here shows that m, and this m is equals to 1 minus 1 divided by m. Okay, so this n and m, they are actually related by this relation. Okay, all right, this is example 3.11. Derive a model function form for CW volumetric CW as a functions of metric suction. Okay, using 3.82. So what is 3.82? Okay, using 3.82, so we try to come up with the model function form for CW. So what is CW? CW is actually the derivative of volumetric water content with respect to metric suction. All right. So this equation, equation is also referring to this one, right? So it's also referring to this one, and this form is used here, right? So if you want to use Ricci equation, you see that there are different variables. Okay, Okay, for example, these variables, okay, this relation between spatial derivative of volumetric water content with respect to metric suction. So this relationship has to be determined. Okay, so you must derive the mathematical equation for this part before you can even solve this equation. All right. So this example is to show to you how, if you want to use Van Janssen equation, how can you get this spatial can get this derivative of volumetric water content with respect to metric suction. So you take the equation from Van Janssen equation. Okay, take it from the Van Janssen equation. So you do the mathematical derivation. Okay, so you conduct derivative on the equation, and then you get the final forms of derivative. Okay, the derivation. Okay, all right. This slide shows to you the graph that I showed you before, and also this parameter used. Okay, so you have a theta saturated volumetric water content, residue volumetric water content, alpha saturated hydraulic conductivity, and also the N. So if you put in all these value for sandy loam and also for silt loam separately, you should be able to generate this graph. Okay, you should be able to generate this graph by using the equation that derived from equation 3.85. So you should be able to rederive the graph by using the data given in the table 3.7. Okay, so if we look at the table 3.7, we have the parameter, and then if we use this parameter, the theta s, theta r, alpha, ks, and n, we place into this relationship this metric suction as a function of volumetric water content, and the k as a function of metric suction. So you can see this graph, it shows the metric potential as a in relation with volumetric water content. So basically it's referring to the metric suction as a function of volumetric water content. So this equation is where you can see the relationship between volumetric water content in relation with the metric suction. Alright, so if you use this parameter theta s, theta r, alpha, ks, and n, you place into this equation, you should be able to reproduce the graph for silt and sandy loam. Similarly, if you want to produce a graph for unsaturated hydraulic conductivity in relation with metric suction, so you use this equation and use the variable provided here, theta s, theta r, alpha, ks, and n, and therefore you'll be able to plot this graph again. Okay, all right, so that's all. Okay, now let us look at the simulation of water infiltration into the soil. So this figure shows the soil depth on the y-axis, so soil depth in centimeter, and then there is a metric potential. Okay, so metric potential is related to soil volumetric water content. So at high metric potential means at very high negative value, so the metric potential very high suction value, so it's very high. The water content is very low. So here we have a low metric suction, so the water content is higher. Okay, so here we have a higher water content, and here we have a lower water content. So as the water infiltrate into the soil, so here we have two different soils, sandy loam and silt. So as the water infiltrate in the soil, you can see that water entering sandy loam, sandy soil is a bit faster than silt, because sandy loam is a bit coarse in size. It means the size a bit bigger, and whereas in the silt, the size a bit smaller, so it's not that easy for water to get in. So let us look into this. So infiltration at constant potential, okay, at constant potential using Van Janssen equation, okay, and Richard equation. So the Van Janssen equation as a constitutive function, as a supporting equation for Richard equation, right? So you need to set the boundary and initial condition. So we know that the top boundary here is top boundary of the soil is negative 15 centimeter. So we see that all of them is nearly negative 15 centimeter. And then at the bottom boundary of the soil is negative 100 centimeter. So you can see that is the value is negative 100 centimeter. Okay, negative 100 centimeter, and then the initial condition is 100 centimeter. Okay, so all of them initially are 100 centimeter metric suction. Okay, metric suction are 100 centimeter. So this is metric suction. So don't be surprised when I talk about metric suction. It also means volumetric water content, because at high suction we have low volumetric water content. At low suction we have high volumetric water content. So it's interchangeable between them. All we need to know is that we need to find out the relationship between metric suction and volumetric water content. All right. So we have that. Then we use the Richard equation to conduct the simulation. That's supported by Van Gansson equation. So this is the outcome of the simulation. So the transition between the wet and dry zone is abrupt and significantly narrower in the coarse texture sandy loam soil than finer silt soil. So in coarser texture like sandy loam, the changes is the water infiltration front. The changes is more dramatic. So, but if you look at the silt, the changes is less dramatic, because coarse soil, water can enter at a faster rate, so the water will be pushed down faster. All right, and that's why the changes is more dramatic. All the wetting zone happening at a very short distance. Okay, so each soil, the wetting front move faster at first and slow down to a more constant speed at longer time. So you can see that initially for T is 1 day. You see that it enters quite a lot. For silt as well, it enters quite a lot. But at day 2, it enters a little bit. See, even for day 2 for silt also enter a little bit, and this continue to be constant as it flow down. Similarly for silt as well. So the infiltration becoming constant as it flow downward. So wetting front shape does not change as it moves downward. So this is what we observe from the simulation by using Richard equation and Van Gansson. Right, now let's look at the infiltration rate versus time for two different soils, sandy loam and silt. All right, so the rate is high. The infiltration rate is high at early time because water is drawn down by capillary extraction and gravity. Capillary extraction is given by this term, the derivative of metric suction with respect to spatial, and then the gravity is given by this one, the plus one. Okay, all right. So at longer time, only gravity is significant. Okay, so as the water infiltrates deeper into the soil, only gravity is significant. So the sandy loam has a significant infiltration rate. So the sandy loam has a more higher infiltration rate than the silt because its hydraulic conductivity is higher at the entry metric potential H0 equals to negative 15 centimeter. So sandy loam has a higher hydraulic conductivity at the entry point of negative 15 centimeter. So we can look at the graph, right? So at negative 15 centimeter, so sandy loam hydraulic conductivity potentially is higher, right? Higher than silt. Okay, so which resulted in a higher infiltration rate. Okay. All right. Now let's look at different flow orientation. Just now we look at infiltration. Infiltration is the water flow from top to the bottom. So water enter at the surface of the soil and infiltrate deep into the soil, right? Whereas upward flow is different. Upward flow is a flow from the bottom to the surface. Okay, from the bottom of the soil to the surface. So here the upward flow is from a water table, so it means groundwater. So the groundwater flow upwards towards the surface of the soil. Also the same, we're using the Van Gansson equation and Richard equation. So we have a boundary and initial condition given here. So at the lower at the bottom's interface, we have a pressure of 0. Okay, the metric suction is 0. At the surface, the metric suction is negative 200. Okay, negative 200. Okay, and the initial condition is all negative 200. Okay, all negative 200 centimeter. Okay, so water move faster in upward direction in the silt. Okay, in the silt, faster in the silt than in the sandy loam, because hydraulic conductivity of the latter, hydraulic conductivity of the sand, okay, become very low in much of the soil profile. So if you look at the soil profile, okay, if you look at the soil profile, the hydraulic conductivity is high initially at low metric suction, okay, but at the other metric suction region, the sandy loam is very low, and compared to silt loam is a lot higher at different regions. Okay, so we can see that silt has a stronger attractions of water towards the the soil has a stronger attraction towards the water than sandy loam at all the other region. Okay, at all the other region. Okay, so that's why it has so that's why the water move outward in silt faster than sandy loam. All right, so here's the day of simulation. So it's simulated until 20 days. So you can see that 20 days the silt already reached the surface of the soil, whereas the sandy loam still has 20 centimeter below the soil surface. Okay, so this figure, the figure 3.20, shows metric potential versus time at different depths. So the depths of -3 centimeter below the soil surface, or -25 centimeter below the soil surface, -50 centimeter below the soil surface, -75 centimeter below the soil surface, and -100 centimeter below the soil surface for sandy loam soil when the surface flux is cycled every 12 hours. Okay, between -3 centimeter per day of infiltration and 0.5 centimeter per day of evaporation. All right, so you can see that. So you can see the first one is actually 0.3 centimeter below the surface. The second one is a -25 centimeter below the surface. The third one is -50 centimeter below the surface. The fourth one is -75 centimeter below the surface, and the final one is -100 centimeter below the surface. So you can see that the variations of metric suction. So the variations of metric potential also refer to the variations of metric suction. It's the same thing. So this also refer to the volumetric water content. Okay, so you can see the water content at the surface. Okay, water content near the surface fluctuate quite a lot. Okay, Whereas at a deeper depth, at -25 centimeter, you can see when it is very dry, because high metric potential, the soil is dry. So when the water enter the soil, so it start to wet, so the metric potential start to decrease. So you have a higher water content. So the water content start to rise, and then start to fluctuate. Okay, similarly with the surface. But if you look deeper, so as the water move deeper and the deeper soil started to get wet, so the metric suction start to drop, and then you can see that kind of what you call that, the fluctuation of the metric potential. Okay, or also you can say as a fluctuations of volumetric water content. So the fluctuation is greater at the surface. The fluctuation at the deeper depth is lesser. Okay, the amplitude is lesser at deeper depth. So you can see that the deeper depth, the deeper we go into the soil, the less fluctuate the value of the metric potential, the less fluctuate for the volumetric water content. I think the same thing we're going to see if looking at the temperature fluctuation at the deeper soil. Okay, so less fluctuation at the deeper soil. So if you go deeper, you can more or less get the average temperature, the average soil moisture content, things like that. Okay, so that's what it means. So this is an infiltration evaporation cycle. The metric potential fluctuate larger near the surface, but attenuate greatly. So attenuate means reduce greatly at increasing depth until the potential is essentially constant at deeper depth. Okay, that's what it shows. Right, so here's another graph. Okay, another graph showing the soil depth changes with soil water flux. Okay, soil water flux centimeter per day. Soil depth is centimeter. All right, so so you can show this water flux as different day. So it's 9.2 day, 9.4 days, 9.6 days, and 9.8 days. So below 75 centimeter, okay, below the cutoff point of 75 centimeter, the flux is essentially constant, showing the validity of the approximation. The amount of attenuation of the wave amplitude moving into the soil depends on the frequency of the oscillation. So if the variation is large, so it takes a longer depth to actually stabilize. If the variations of the amplitude is small, so without going deeper, the water flux already started to stay constant. Right? That's what it means.